Hi, my name is Janaye Figge. This poster is over my master's research. The research looks at lake water microbiota and responses to additional nitrogen. Primary producers are known to drive biochemical processes. However, excess nutrient loading can lead to primary producers growing unabated, which can degrade water quality. Therefore, understanding the development of primary producers induced by excess nutrients is critical. Therefore, we asked two questions. First, what form of nitrogen fuels phytoplankton growth? And second, how does the lake bloom history affect the potential for nitrogen to stimulate a bloom? To answer these questions, we ran a 3-week greenhouse experiment where we filled 300-liter mesocosms with lake water and then manipulated nitrogen. To test our first question, we imposed different nitrogen additions on the mesocosms. The nitrogen additions reflected land use. The high nitrogen concentrations resembled nutrients that would be coming in from an agricultural stream, and then the lower nutrients represented nutrients that would be coming in from a grassland stream. We also had control mesocosms filled with just only lake water. To test our second hypothesis, we used lake water from two different lakes, a historically mesotrophic lake, so usually lower nutrients, and then a historically eutrophic lake, so higher nutrients. These two lakes with opposing lake histories were used to assess if baseline nutrient levels and microbial community shifts toward a cyanohab under the nitrogen pressures. We sampled for a sweep of variables. However, today we will only be looking at the chlorophyll A, microcystin, and the microbial community in both the water column and in the sediment samples. We found that chlorophyll A had a higher response in the eutrophic lake than in the mesotrophic lake for both the water column and in the sediment. And then overall, microcystin concentrations were low. Figure A is a principal coordination analysis graph. So each point represents a sample. The closer together those 2 points are, the more similar that sample's microbial community composition is. The further apart those two samples are, the more dissimilar those communities are. On sample day 3, the lake's microbial communities are organized in distinct and separate clumps. So the eutrophic and then the mesotrophic. On sample day 9, the lake's microbial communities are still different. However, the eutrophic lake is starting to move across axis 1, and the mesotrophic lake is starting to move up axis 2. On sample day 3, in the eutrophic lake, the nitrogen additions are becoming more different than the other nitrogen additions. The shifts in the microbial community in the eutrophic lake are largely being driven by the nitrogen additions as we continue to see those differences in the nitrates. And then in contrast, the mesotrophic lake is moving up in a single clump. Therefore, changes in the mesotrophic lake is more driven by time and not the nitrogen additions. Figure 5 is looking at the relative abundance of the cyanobacteria phylum. Abundance is higher in the eutrophic lake than in the mesotrophic. There are more chloroplasts relative to the other cyanobacteria genera. In the mesotrophic lake, chloroplasts are more indicative of a green algae bloom. Therefore, the microbiota in the mesotrophic lake is favoring the green algae bloom more, or favoring the green algae bloom more than the blue-green bloom. Our experiment showed that nitrogen stimulated non-toxic blooms. Therefore, management strategies should be aimed at alleviating eutrophication by managing for excess nitrogen. Thank you.